Like, you know how you just close it?
All right, let's take a look at lesson 10.1. Before we do so, let's review kind of where we were. And this is kind of the piece. We're jumping to chapter 10, but we just finished chapter 3. You might be thinking, why does Dallas pair chapter 10 or follow chapter 3 with chapter 10? And here's kind of why. It's this idea. So I'm going to give you this problem, and it'll kind of lead into where we're going. It says here, 2 ant colonies are growing at the exact same rate. The first colony, however, has a larger population than the second colony. The equation F there illustrates the population of the first colony. Number 1, what equation represents the second colony if G is 85% of the size of F? So let's just first start with, do we understand what's going on? Given this equation here, the equation F, get my pen working. Given this equation F, what do the pieces of information in that equation refer to? For example, what is the 300 refer to? That's the initial. Very good. When we dealt with exponential, the front value was the initial, and in this case, it would be initial population. So I'm going to just say initial pop. Okay, what did the second value have to deal with, the 1.03? The rate. And the formula is technically, if you simplify everything down, it's 1 plus or minus the rate. So in this case, what is the actual rate? 3%. So R would be 3%. It's a growth rate. And then the population, I guess I should have put that in there. The initial population equals 300. Okay. This says what equation models?
And happy Friday, teachers.
So as it's saying, it says number 1, what equation models the second colony G if G is 85% of the size of F? Okay, so if it's 85%, does that mean I'm changing the actual population, or am I changing the rate? So the rate's changing? So it's changing population because also, go back up to this first sentence. 2 ant colonies are growing at the exact same rate. So the rate does not change. What's changing is the initial population. So if G is 85% of the F, we take the 300 and say, what is 85% of 300? So 85 times 3. Let's go open up Desmos. I'm just going to be short here. I'm going to click on my page, Desmos pre-programmed graphs, and I'll choose a blank graph. If it opens, 255 is what I'm hearing. So remember, if you don't know how to do percentage, just divide it by 100 like that, and it is 255. Yeah, so if that's the initial population of G, that's G's initial population. G's initial pop. Then the equation would then be G of T equals 300, not 300. What's the initial population? 255 times 1.03 to the power of T. You got it. That would be my equation for number 1. Now, another way you could use the calculator to help you out is you could say that G of T equals 85%, which you could just say 85 over 100 times F of T. You could have typed it in like that, and that would have worked as well. That would have graphically shown you the correct answer, just so you know. Let's now look at number 2. It says, draw a first quadrant sketch modeling the populations of F and G over time. So let's go graph these. I'm just going to slide my picture over. So F of T equal 300 times 1.03 to the power of T. And then G of T equal 255 times 1.03 to the power of T. Question for the students. I want y'all to think about it for a second. Why can I not see any graph right now? The initial value is 300 and 255. My y-axis, can I see that high? No. And T refers to, in this case, the x-axis. That's my independent. Can I have negative time? No, so really that's why I want first quadrant. It's real world. I'm only looking at positive times and I should have positive number of ants. So I'm going to change my settings here. I'm going to change this to a -5 and we will look at the first 15 years. The reason I leave x-axis, I hit the settings in the top right, by the way, if I didn't say that. Hit that little wrench up there. I'm going to change it to 15. I left it -5 so you can see the y-axis. We need to have a minimum value of 255. But I want to see this axis. So I'm going to say -5 here, just so I show it. But up here, if the minimum I need to see, I need to see at least up to 300. I'm going to pick a number bigger than 300. We all want to say like 500. Let's do 500. So when I put in 500, here's two graphs, and I can't hardly see my x-axis. So I'm actually going to change this just a bit more. My y-axis, I'm going to make sure I can see a little bit of that. And I'll go ahead and raise it a little bit higher so I can see more. There's the idea of the graph. That would be the first 15 years of this growing right here. So here's your picture for all of this. Scan it, put it in our notes. You need to just have some type of sketch on your paper resembling that. Starting at 300 and 255, and it would be curving up at a rate of 3% growth. 3% growth. And that would suffice as your first quadrant sketch. Moving on, chapter 10. We're going to look at representing arithmetic and geometric sequence using recursive formulas, among other things today, as well as sigma notation. Overall, we're starting a chapter on sequences, series, and sigma notations. That's what we're looking at. So the first thing I want to point out is I want you to know a sequence is anything with a pattern, but the sequence, each individual term is just that. It's individual. That has no relation on the next term. So for example, here's a sequence. Let's see if you can figure out what comes next. 3, 6, 9, 12. Okay, that would be a sequence. Now, a series might be a little bit different. A series might be like this: 3 plus 5 plus, you can take a guess? 7 plus 9, and so on. So you might look at them and say, well, they both have a pattern. That's true. But there is a different symbol I put between the two. What's the difference in the symbols? The commas. In sequences, each term is just individual. It has no relation on the other. On a series, you're getting to a sum. A series will add or subtract together, and you can either way total it up. So they relate to one another in that regard. So that's the difference between a sequence and a series. Is a sequence will be separated by commas. A sequence will be separated by commas. A series will be separated by pluses or minuses because they're going to get to a total. Okay. Finite, infinite. Finite means it does not go forever. This was finite. If I wanted to make this one infinite, I would do this. And now it's become infinite. So that would be finite. This word right there, finite. That's infinite. And all this other stuff we'll talk about as we go. All right. So here, a little pattern recognition. Example 1. 3, comma, -1, comma, -5, comma, -9. We're tasked with finding the next 4 terms. What's happening each time? It's subtracting by 4, you're saying?
Yeah.
If you're not sure, a good way to check is a symbol for this is we're going to call the first term A1. Okay, just go ahead and mark that in your notes. This would be good for later. What do you think we'd call the second term? A2. And the third term? A3. And finally, the fourth term? A4. Okay, what you're going to learn that if you're solving for an arithmetic series, that means something that is adding or subtracting. If it's arithmetic, basically the formula is this: you take any number and subtract the previous. So I'm going to use very generic symbols here, and I'm going to say it's AN minus AN minus 1. With that the n minus 1 and the n's being subscripts, they're written real low. It's kind of like the shift minus of a log. Remember how we were doing shift minus? Now, what this means is you take any term, right on here, any term, and you subtract the previous term. This right there is the previous term. That's what it means by a sub n minus 1. It means the one that came right before it, the one that came one number before it. This would be the previous term. Does that make sense? Yeah. So in this case, if we wanted n to be 2, a sub n minus 1 would be 2 minus 1. You follow what I'm saying? If n is 2, just trying to making sure you understand these symbols. If you just said, hey, I want n to be 2. If n equals 2, then when you would subtract the next one, it would be 2 minus 1. So if n is 2, let me do this clear. If n equaled 2, then you would say, hey, I want the second term minus the first term, which in this case would be negative 1 minus 3, which we would get the negative 4. And that is what it's changing by. That we'll call a common difference. Okay, so what I'm going to do now I erase this, I'm going to come back here and put equals D, and we're going to say the D stands for the common difference. I'm really getting into next class, but I just want to set up where we're going. That's called the common difference. In this case, we have a common difference. So I'm talking a whole lot more than I have to. We could just get our answer. Before I move on, since I've already done this much of an introduction, I'm going to go ahead and give you geometric. Geometric is when they multiply or divide. So geometric means you're taking your second term or any term and you divide it by the previous term. That's how you'll find that, and that will equal what we call R, where R is the common ratio. All right, so that's going to be how we're going to determine, ratio. That's how we're going to determine our values here. But you've already told me you can tell it's being subtracted by 4. So let's go ahead and write out the next 4 terms. What comes after the negative 9? Okay, I'm just going to cover this up so I can write it on there. Let me cover that up. So the next 4 terms would be negative 13. Then we subtract 4 more. Negative 17, subtract 4 more. And subtract 4 more. Negative 25. Okay, there's the next 4 terms of the sequence. Quick quiz. What would you call a sub 25, negative 25? A sub what? 8. A8. Why would it be A8? 1, 2, 3, 4, 5, 6, 7, 8. You see how that's the 8th one? That would be A8. What would negative 17 be? All right, you got it. That would be A6. What can AN represent?
Any number.
Any number. So what is AN minus 1?
The one before.
1, it came before it. What would AN plus 1 be?
One after.
1 after it. You got the pattern. Okay, good. All right, part B. Let's speed it up a little bit. Uh-oh, my board just turned off. Let me power on. All right, part B. It says find the next 4 terms in this sequence. All right, take a look this time. What do you notice is happening? It's subtracting again. What's it subtracting by?
On the first one,
3. Okay, so we're just subtracting 3 every time?
No.
No, this is not. It's changing by something else. What's happening the next time?
5.
It's minus 5. And then the next time? 7. You'll learn this is a quadratic sequence. This is quadratic. And that means it's going to have more to it.
You subtract like 2.
And you're 2 more than the previous term. So if we want to find the next 4 terms, I'm just for now going to put quadratic. And we'll come back to the formula later. That's just the name of this. This is a quadratic. What did you call this? A sequence or series? Are they separated by commas or pluses and minuses right now? Commas. So this would be, since they're separated by commas, this is a sequence. This is a quadratic sequence. Okay, so the next term, if we now subtract 9, what is 3 minus 9? Negative 6, good. And what would we subtract next? 11. So what will we get? Negative 17. Okay, what will we subtract the next time? Subtract 13. Whoops, forgot the 1. That gives us negative 30, I agree. And one more. We now subtract 15. And so the value would be negative 45. So this is a lot of patterns. Chapter 10 is pattern recognition. All right, just make sure you're clear. What would -6 represent in sequence or series notation? Sequence notation. That would be A5. Good. What is 18?
A1.
A1. All right, great. That brings us to the next one. Here, this is, by the way, this is a cubic sequence because the power is a cube. Cubic sequence. You can name that. I'm giving you extra information just because I want you to be smarter than the textbook. That's what that's called, a cubic, because it has a power of 3. If you found out the equation that would generate all these, it would be quadratic. The reason, by the way, I never finished this. The reason I know it's quadratic is because what happens is you see how this is how it's changing each time. The second level is the same all the way down. How much are all of these changing by? -2, technically. So since they're all -2, since you see how that's the second level, that would mean you need a second power if you were writing an equation. And that's why I knew it was quadratic. Quadratic means x squared or power squared. Because this was second level, and that's what's going to happen this time. When I find the first 4, and I'll actually make this, let's scratch this. Let's make it the first 6 terms. So I can show you that it's a cubic will be third level. So the first term, what would A1 equal? If we plugged in a 1 for n, A1 would equal 1 cubed plus 1. I agree. What's 1 times 1 times 1? 1 plus 1 more? 2. Okay, if we wanted to find A2, what I'm doing is I'm substituting in the formula. If you didn't catch what I'm doing, I'm plugging in the 2 for n. Okay, we would have 2 cubed plus 1. 2 times 2 times 2 is 8 plus 1 more? 9. Okay, third term would be 3 cubed. 3 times 3 times 3. Wow. Y'all agree with Josue? 3 times 3 is 9 times another 3. 27 plus 1 more. That is 28. Okay, A4. 4 cubed. 4 times 4 is 16 times another 4. 64. Add 1. 65. Could you be typing these in the calculator? Yes. Okay. Here we go. This one might be a little bit harder. 5 times 5 is,
25.
so you multiply by another 5. It's 125. Add 1. 126. And finally, 6 cubed plus 1. 6 times 6 is 36. Times another 6. I'm getting 216. That might be bad math.
Yes.
216. We add 1 more. What do we get? 217. Okay, there's our first 6 terms. The way you would normally write these out, though, is if it's a sequence, you separate them by commas. So 2, 9, 28, 65, 126, and 217. Now that's our answer. So I'm going to go ahead and circle this up. That's our answer. But now check this out. I want to show you why we call this cubic. It's because it'll be third level. What's the difference between 2 and 9? Add 7. What's the difference between 9 and 28? Not 21. 19. Okay. Next 2. I'm getting 37. The next 2. 61 maybe. And here. 91. Y'all are just okay with my numbers? We're about to find out if I'm right or wrong real quick. Okay. All right. Let's go to the second level. So I'm saying this is cubic. It'll take 3 levels. What's the difference between these 2? 12. Good. What's the difference between these 2?
I'm not doing this.
18. What's the difference between these 2?
Oh, yeah.
24. What's the difference between these 2? 30. Okay, let's check third level. What happens? What's the difference between these 2? 6. What's the difference between these 2? 6. What's the difference between these 2? 6. If you're ever wondering, how does the calculator, if you were going to use Desmos graphs, how does it come up with these regressions and models? You remember this calculator where you turn in a table? What it does is it does this math And what you find out is there's certain rules that mathematicians have discovered that if you have this same third level, we know it's cubic. And this, I believe, is equal to 2a. So if I typed in this sequence, I think I would have, if 2a equals 6, a 3 in front of my cubed. I'm going to just test that real quick for kicks and giggles here. Our numbers, we had 1, x was, the n value was 1, 2, 3, 4, 5, and 6. And what do we have here? Oh, it's on the side of my paper. 2, 9, 28, 65, 126, 217. If you went down to not quadratic, but cubic, it says my a is, well, that's just not working right. Why did that not work? Oh, it's saying it's perfect. Well, my a is 1. So apparently 6a equals this number. Whatever it is, that's how you would do it. That's what the calculator is doing. So I obviously I don't remember that math very well, what that started off with, but that's how it works. So you got the theory of it. You can do your own research on what each value represents from there. But that's how it does it. With your DOL, I keep it much simpler. I want you to find the next 4 terms given this sequence. DOL number 1. All right, let's take a look now at example 2. So example 2 says, we're going to now talk about recursively defined. Now this word recursive means you have to solve the sequence, you have to know the previous number. That's what that means. Like it's going to use the previous number to find the future number. That's what recursive is. So you use the previous number, use previous term. I shouldn't say number, I should say term. Use the previous term to find future term. Now there's also a thing called an explicitly defined, and that is you can find any term at any time. But recursive means you need to know the previous to find the future. So here it says find the 4th term of the recursively defined sequence. They give us 3 pieces of information. They tell us our first term is 3. That's our first piece of information. They also give us the formula, and they tell us that n has to be greater than or equal to 2. So we know our first term. Our first term is 3. Do we know the second term?
No.
Now, if you want to find it, what you do is you would say, okay, n has to be greater than or equal to 2. So I'm going to plug it in and just say, I want n to be 2. So I'm going to for a second say n equals 2 right here. I know I haven't done it that way today, but I'm going to do it right now. N equals 2. Now, if n is 2, then this will be 3 times, what is a sub 2 minus 1? This would be saying, what if n is 2, what's n minus 1 going to equal?
At A1.
A1. So it'll be an A1 there, minus the n. What do we say n is? 2. I'm going to substitute parentheses, plus 2 more. Okay, now, what is A1 in our problem? 3. So I'm going to replace this. Whoops, I meant to change colors. Try this again. I'm going to substitute this, and you know what? To make more sense of this, I'll put an n right here. We're going to substitute in our numbers. We're saying A1 is 3, and n is 2. So if I wanted to simplify, what's 3 times 3? 9 minus 2 plus 2. Those cancel out, and so our number is going to be 9. A2 is 9. Now we're supposed to find our first 4 terms. So now that I found the second term, guess what I can now find? The third term. So to find the third term, here's what I'm going to do. I'm now going to treat an as being equal to 3. So to find the third term, what I'm doing here, okay, I'm going to change one more thing just to make my notes consistent from here on out. The formula says an, and we substituted in a 2 there. Okay, so I'm going to just copy down the formula. It says an equals 3 times a sub n minus 1 minus n plus 2. On this case, what are we going to say on this second? On this time, we're saying that n is 3. So A3 is going to equal 3 times This is going to be A2. Now, what is A2 equal to? 9 minus what's in? 3. Okay, so now let's simplify. N was 3, so that N is 3. What is 3 times 9? 27 minus 3 plus 2. What's 27 minus 3? 24 plus 2 is 26. That's our third term. We're going to do this one more time. We need to find our fourth term. So again, what I'm going to do is copy down my formula as it was given. AN equals 3 times A sub n minus 1 minus n plus 2. And we're going to substitute. So in this case, n is what number? 4. N is 4. This is the fourth term. So n is 4 this time. What is A sub 4 minus 1 going to equal? A sub 3, which is 26. This is now a 26 here. What is n this time? 4. So when we go to simplify, 3 times 26, 78, I believe. I'm going to use blank graph here. I think I already have one open. Yep. 3 times 26 is 78. So it's 78 minus 4. What's 78 minus 4? 74 plus 2 more? 76. That's our solution right there. That's the fourth term. Okay, so in a nutshell, recursive, when you see that word recursive, that means you have to find them in order. So to get to the fourth, we had to know the third term. To get to the third, we had to know the second term. And to find the second, we had to know the first. They gave us the first, they gave us the formula, and they told us what n, where to start with n. We started with n of 2 and moved on from there. That's what this was telling us. Start with n of 2 and make n just grow bigger one at a time. And so that's how I solved that. Now I have one for you to try. Same idea, except this time you're going to find the fifth term. I want you to find the fifth term, and you're given this formula. Okay, so I'm giving you the first term of 28. So a little reminder, you're going to have to find the second term, and then you'll find the third term, and then you'll find the fourth term, and then finally you'll find your fifth term. And you'll be using this formula all along the way. DOL number 3. Now let me introduce to you the Fibonacci sequence. So you're going to want to see this here. It says, suppose that a stem has to grow for 2 months before it's strong enough to support branches. At the end, of the second month, it sprouts a new branch and continues to sprout one new branch each month. The new branches grow similarly. How many branches will a plant have after 18 months if no new branches are removed? And there's the table representing what's happening. And I'll just give you a little drawing at the bottom. Let's say the ground is this blue stuff at the bottom, and a tree sprouts up. So here's my tree. I don't have a brown, but here's black. So the first month it sprouts up. What this is saying is it doesn't grow any branches the first month. It takes 2 months before it sprouts anything. So there's 1 month. Here's 2 months. It grows. After 2 months, guess what happens? When it goes to grow the third month, it sprouts. It has a branch like that. So that's 3 months in. It's grown 3 times straight up, and it has one little sprout. Well, in month 4, not only does this grow up, it also sprouts another branch. And guess what this one does over here? It grows itself. On month 5, this again grows tall. It sprouts. This grows taller, but this one's been growing for 2 months. So guess what this is going to do? It's going to sprout its own as it grows bigger. On month 6, a guy named Fibonacci noticed this. This is how it occurs. This grows, this sprouts, this grows, and it sprouts because it's been growing for 2 months. You see here. And this one grows a second time. This one grows and sprouts. You see how it's starting to look like a tree? If you ever wondered how do I draw a tree, now you know. Okay, next month, I'll do one more here. I think that was that month, 6 months in, however many months I've lost track. Month 7, let's just say it grows, it sprouts, this grows and sprouts. This grows, sprouts, grows, sprouts, grows, sprouts, grows. And so if I'm on 7 months, I should have 13 total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look at that. You see how that's a 13? Fibonacci came up with the sequence to mimic how trees grow like this. Can anybody, now that I've been doing all this tree grows sprouts, can anybody figure out what the pattern is? And I'll go 8 months here. Grows, sprouts, grows, sprouts, grows, sprouts, grows, sprouts, grows. I can't remember if I grew that one or not. I don't think I did. Grows, sprouts, grows and sprouts, grows, sprouts. This one grows and sprouts. So on month 8, I should have 21. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Get it right. Did anybody figure out the pattern while I was drawing my tree? Okay, I'll give you a hint. It's doubly recursive. Doubly recursive. Well, as y'all debating here, I'm just going to go ahead and tell you. So I said it's doubly recursive. What I meant by that is recursive. Remember, that means you need to know the previous term to find the future term. Remember, that's how I said recursive works. Doubly recursive, you need to know the 2 previous terms to find the next term. So basically, it's like this. You take 2 terms together, and the 2 terms together create the next term. And this is, and like I said, Fibonacci, notice this watching tree growth, that this is how a lot of plants actually grow. And you can see that this pattern matches up the math. It's crazy that the math matches up this way. But as you go through, if you add up the 2 previous terms together, you can get the next term. So 1 plus 2 is 3. 2 plus 3, does that equal 5? Yeah, 3 plus 5, does that equal 8? Yeah, and you could go all the way down the list. Does 34 plus 55 equal 89? Yes, it does. It works all the way down. So we want to know how many branches will a plant have if no branches are removed after 18 months. So what I'm going to do on your paper, if you take your pencil and you say, you right click like I just did and say unlock, just slide it over this way so you have space to write in. We're going to go till month 18. So here we go. I'm just going to delete that. Month 18. Let me get some lines in here too, so I can draw these straight. All right, in month 14, we would add these 2 terms together. What is 144 plus 233? Some mental math geniuses. 377. Okay, month 15. And you'll want to write down this list though somewhere. You'll want this. Month 17. You add these together. 15, I'm sorry, month 15. 7 plus 3 is 10, so I need a 1. That's 8 plus 3 is 11. I'm getting 6. 610. 610. I'm trusting you. Don't make me draw it. All right, month 16. We add those together. 987, great. Month 17. Add these together. I know we'll have a 7, 9, and 15. 1597. And finally, we got to month 18. Add these together. It'll end with a 4. Add 1, 10, 18. Add a 1, 6, and 9 is 15. 2584 is what I'm getting. This would, in month 84, there should be 2,584 branches in month 18. All right, so I told you, I hope you wrote that down. Why did I tell you I hope you wrote this down?
The next question.
Because your DOL, you need to find in month 20 what the answer is. DOL number 3. Now we move on to convergent and divergent. What this means is these sequences or series, if it's that, will they be approaching the x-axis, meaning approaching 0, or are they approaching positive or negative infinity? And so all this is going to be determined by the rate. And here, remember, this is how I told you this is built off chapter 3. You have the initial amount. Here is your rate. It's all built off the rate, but I'm going to show you graphically, and then I'll just tell you the easy formula. So graphically, here's how this works. Our original problem here, I'm going to say y instead of an. I'm going to say y equals negative 4,000 to the power of negative 1/4, or not power of, times negative 1/4 to the power of x. And I'll press the home screen here. And I saw it, but it disappeared. You see these little dots? It's trying to graph it. It's struggling because of the rate being negative. But what you can do is if you hit table and I start pressing enter, what's going to happen is it'll start plotting these. And you can see when I zoom out, what is my sequence doing? Is it getting closer and closer to 0? Or is it farther and farther away from 0 as we go? Yeah, you see how it's getting really close in on 0? That means this is converging. It's converging. If you think about driving, I lost my illustration I was about to say, but it's a lot of times we merge onto a highway or converge onto the highway. That means you're approaching the highway. That's what's happening here. This is converging. So this is converging. And here's the rule. Converging since the rate or the base, let me say it that way, since the base is less than or equal to the absolute value, let me say it this way, the absolute value of the base is less than 1. If the absolute value of your base, so ignore the negative doesn't matter. If the base itself, the absolute value of that base is less than 1, it's convergent. So the math here is the absolute value of negative 1/4 equals 1/4. And that is less than 1. That's why it converges. Does that make sense? That's the math. You go off your base. It's always the base. Divergent would mean your absolute value of the base is greater than 1. All right, so part B. And again, I'll show you these graphically as we go. Which one's the base on part B? Negative 2. What can you tell me about negative 2? The base is negative 2. So the absolute value of negative 2 equals what number? 2. That is greater than 1. So guess what that means? Divergent. Since it's greater than 1, it's divergent. Now let me show you graphically. What I'm going to do here is just change my equation to, I already forgot what it was. There was no number out front. It was negative 2 here. And we divide everything. So we need to divide this whole thing by 2. So look what's happening to my list here. Do you see how the dots are? What are the dots doing? Are they getting closer and closer? No, they were not. They were getting further and further away. And I could have started this list like at negative 20. And it's not really cooperating. I was hoping it would just, if I could press enter. And if I started doing all these in here, you would see that if I zoom out to the left, you'll see how it gets really close over here and it takes off. So that's why it's divergent. It's leaving the x-axis from left to right. All right, part C. What is my base? Again, base always has the power. What's the base? Okay, 0.1. The absolute value of 0.1 equals 0.1. Is that less than or greater than 1? Less than 1. That means it's going to be convergent. Oops, I meant to write the word since. Since it's convergent, since the absolute value of 0.1 is 0.1, which is less than 1. Which brings you to your DOL. Now, example 5, it tells us find the fifth partial sum. What that means, when it says find the fifth partial sum, by symbols, this means to find S5. Now, they use the S to represent the sum, and what that is it's A1 plus A2 plus A3 plus A4, hey guys, plus A5. You would add those 5 terms up. If you add those 5 terms up, you get the fifth partial sum. Now, there's a formula for this, okay? And I'm going to skip a few slides in a way to tell you how you do this. If you have a formula, you can find the sum by using this called sigma. Let me change it here to colors. Sigma. And here's how sigma works. Sigma is going to take the lowest value term that you're adding, which in this case is A1. So what I'm going to do is say n equals 1, and you put the last number on top of the sigma, which is 5. So I want to find 5 sums from A1 to A5. So I'm going to do A1, n equals 1 all the way up to 5. And what I do in the parentheses is I replace the right side of the formula. So it's going to be n squared minus 3. So instead of saying an equals, what you'll do in the future is you'll scratch that out and do sigma in its place. Sigma, and we'll replace the an equals. There's the n equals, and instead of it being an a, we're going to do a sigma, which kind of looks like an s somewhat. So if we type this in the calculator, this will give us our solution. So I'm going to go over here, and I think you can type in sum. If you just type in sum, S-U-M, it gives it to you. Or you can go to Desmos calculator, hit functions, and on the MISC tab, you'll see it down at the bottom. But you can just type in SUM for sum. You say n equals 1, and we're going up to 5. Now, what is that actually going to do you think? What is that telling the calculator? It's going to plug in all those numbers. It's going to count. So what it's going to do first is plug in into our formula, n is 1, and get a value. And so if it plugged in n is 1, let's just figure out what all these equal. A1 would equal 1 squared minus 3. A2 would equal 2 squared minus 3. So what it does is it just plugs all these in and then adds them up. A3 would equal 3 squared minus 3. Whoops, minus. And then finally, not finally, I got to find 5 of them, sorry. A4 would be 4 squared minus 3. And now finally, A5, what that equals is 5 squared minus 3. Now the calculator does this really fast for us. What it does is it takes in all these numbers and it adds them up. So like I said before, the sum, I'm going to do S, capital S, shift, minus, then a 5. That equals A1 plus A2 plus A3 plus A4 plus A5. You see how it says that was 40? That's exactly what the calculator told us up there. You see how that is also 40? Do you see that? Desmos did that really fast, did it not? So that's definitely the best way of getting your answer. I'm going to go ahead and write these out. Give me a moment here so you can have it for your notes. Man, that went way big. I didn't mean that to be that big. Perfect. Okay, so what it did there is it plugged in all the numbers and it found out A1 was -2. So it had -2. Let me do this like in blue. A1 was -2, and then it added 1. A2 was 1, and then it added 6. And what do we have? 13 and 22. A4 was 13. A5 was 22. When you add those up, you got 40. Thus, the answer was 40. That's the sum. And so the way the answer would be written is S5 equals 40. S5 means it's a sum of 5 terms. Okay, so again, That's the easier way using the calculator of how to type that in. And that's what it does. It just plugs in all the numbers. So it goes through plugging them in. Okay. Part B, S of 4 equals this. Y'all know the shortcut? What could I do shortcut wise to get my answer? What would I actually type in the calculator? You would type sum, which would give you this symbol that looks like sigma. There you go. Then what do I type in on the bottom? And it says n equals, what would you type? So like if you're going to do this on your own, you'll come back up here and you'll type in sum, S-U-M, S-U-M, and it shows you this. What do you put at the bottom of your sigma? 1. That's the first term. How many terms are we going to have? 4. What do I put on the right side? Typically, it helps to put in parentheses. 6 divided by 2 to the power of n. That's our number. How do I change this to? I did n to the n. 2 to the n. How do I get this as a fraction? On the left in the blue, press the fraction. The answer is going to be 45 over 8. So 1 to 4 of 6 over 2n equals 45 over 8. Again, what the calculator did is it took the first term, which when you plug in a 1, it'd be 6 divided by 2 to the first, which is 6 divided by 2, you get to 3. And then it plugs in a 2. So 6 divided by 2 squared, that's 4. So it'd be 6 over 4 or 3/2. A 3 would be 6 over 2 cubed. That's 8. So 6 divided by 8 is 3/4. And a 4, the fourth term, what it does is it plugs in an n of 4. That's the math that's happening, which would be 6 divided by 16 or 3 divided by 8. When you add those up, you get your sum. And that's where we got the 45 over 8. When you add all those terms up. Does that make sense on how the math works?
Yeah.
Yes? You sure? All right, your turn. I want you to find the fifth partial sum. I would just use the calculator if I were you, because it does not make mistakes. The calculator replaces the sigma, I should say. The sigma replaces an equals. That's what gets removed, and you use the sigma instead, and it'll solve it for you. DOL number 5. Okay, again, if you're not getting the right answer, try putting a parenthesis around the whole thing when you use your sigma. It might make a difference. Put your sigma right here, and then that parenthesis, like that. Okay, so now we actually get to the spot in the lesson where I'm supposed to show you sigma. And so just some names. The bottom thing is called the lower bound. That right here is the lower bound. If you want to mark that, that's the lower bound. That's what they call that, which obviously makes the top one become the upper bound. The n exactly that you're plugging in would be called the index. That's what they would call that. Over here, it's the equation. Now remember, what we were just doing is you substitute the equation. So in our previous problem, we said an equals, I think that DOL said 3 to the power of n minus 2. What you're doing is you're removing the an equals, and since it's equal to this, you're replacing an with that value right there. That's what we did on the previous problem. That's how that works. Okay, so sigma. We can plug these in. Let's get some solutions to make this easier. I'm going to shrink my screen just a little bit and shrink this one over, and let's find these 3 values. So from 1 to 4, value n squared minus n. So I got 20 for the first one. Is that what y'all are getting? What do you notice is interesting about number 2? What's different about it than all the others?
No parentheses.
There is no parentheses. That's one thing. But am I starting at 1? We start at the second term. We were adding up the second. I'm going to hit decimal here, and I'm going to get a fraction. Oh, I put plus 2. I'm sorry, plus 3. There we go. And finally, part C. What's different on part C? There's an infinity. Now, heads up. There is an infinity key, but it doesn't work for this unless they made an update since last year. Let me check it. There is an infinity key, or maybe you just type in infinity. Yeah, if you type in infinity, does it give you your answer?
No.
No. So what you can do is substitute with a really large number. What number should we substitute with? I start with 1,000. Put 1,000 right there. If you put in 1,000, see if it'll give you a value. When you go fraction, what's it say the value is? 1/3. That is going to be your answer. So those are our 3 answers right there. Notice I did just substitute in over there. All right, so notice for infinity, for the calculator, substitute 1,000. Substitute 1,000 for infinity. I start there. Sometimes it'll say too complex, and if it's too complex, maybe try 100, something like that, to get your value. All right, your turn. Try DOL number 6 here. DOL number 6. All right, let's take a look at how this might look on the ACP. So we have a problem here that was released, that was on one of the released questions. It says, what is the sum of the arithmetic series given there? How would you solve that? I should point out we've moved on to series because series means you're adding or subtracting. So anytime you're doing a sigma, it's not a sequence anymore. It is a series because you're adding them together. You would just type this in. So on this one, I would type in what's the shortcut on the keyboard to type in to get sigma? Sum. Just type in sum. If you don't, this one says K. Change it to K. K equals 1 to 15 of 3K minus 2. So if you just type it in with a K, it should solve. If you want to use ends, you need to substitute all K's with ends. But the answer I'm getting is 330. So 330. 330. If you ever have to take a paper form test again, that's how you would do it. You need to make sure you bubble in. Doesn't matter what you start on. I just start far left. You don't have to do the positive, but you can if you want. 330. That's your answer there. And now, finally, the last one. And I want you to think on this one for a little bit. It says here, Holly is trying to solve a summation given here using this formula. She substitutes the values n equals 4, a1 equals -68, and an equals -56. This formula is on the formula chart, by the way. To discover this sum, what can be determined about Holly's work? And there's these 4 options. So let's first find out, did she get the correct answer? What is her actual sum that she got in her work? According to the problem, what did she get as her sum? -448. Let's go see if that's even right. So let's first check that. I'm going to type in this formula. So it was K of 9 to 13. And the formula said 13 minus K squared. 13 minus K squared. Did she get the right sum? No. So the sum is supposed to actually be, what was that, -550? -550. Okay, so is her answer correct? No. So it's not, the correct answer is not J in this scenario. Her answer is not correct, it's incorrect. So one of these things has to be wrong. How would you find the first term? You would actually not plug in a 1. That's why I want to talk about this. You don't plug in a 1. Look up here on here. The very first one, you don't plug in a 1. What do you plug in first? A 9. To find A1, you would plug in a 9. A1 would equal 13 minus 9 squared. So let's plug that in, see what we get. What is A1 equals 13 minus 9 squared? What do we get? -68. Is that what she got? Okay, so that's not her error. That part's correct. AN, when you just see AN by itself, typically that means any term. But if you see AN in a problem like this, it would mean the last term. The last term, you would plug in the 13. So AN would be 13 minus 13 squared. AN, I'm not sure if it's going to let me do this, is 13 minus 13 squared. Oh, it did. So negative 156. Did she make an error here? No, that part's correct. So that means her error must be n of 5. What does n refer to? Think chapter 3. What does n always refer to? The number. The number. How many numbers are between 9 and 13? Let's see. That's what y'all say. There's 9, 10, 11, 12, and 13. How many unique numbers are there? I shouldn't say n equals. N comes from these. How many unique terms are there? 5. So there's 5 terms, not 4. That was her error. Is she looked at that and thought it was going to be 4? Now, check this out, please. This throws off students all the time. If they don't start at 1, the number of terms is not 13 minus 9. Because if you did that, you eliminate 9. When you subtract by 9, you eliminate the 9. We actually count the 9. So the formula for this is the upper bound minus lower bound plus 1 more, because you don't want to eliminate that. So for example, the previous problem, how many terms would be here? This one's easy because it starts with 1. How many terms would be there total? Just think in general. If you start at 1 and count to 15, how many are there going to be? 15. But if you tried the same math, what's 15 minus 1? You see how that's only 14? It's because it takes away the 1. Subtraction takes it away. So the formula is top upper bound minus lower bound plus 1 more. So this would be 15. This would be 5.